Okay, we want to talk about the phase differences between voltage and current for inductors and for capacitors. This is phase difference given an alternating current. So we should probably label this for alternating current. Alternating current means that, for example, either your voltage or your current is going to equal some maximum value times the sine or the cosine of omega t, possibly plus a phase angle. So, in both cases, we're going to assume a current that's equal to a maximum current multiplied by the sine of omega t, here and here. Okay, so you should pause for a minute and figure out what the result will be. We know that the voltage across the inductor is L di dt. So what is the function? Don't look. What's the function that describes the voltage as a function of time given this current? Okay? Hopefully you've done that. And then you should go ahead and kind of quickly do the same thing for the capacitor. Again, we're going to assume that I is I max times the sine of omega t. If you're trying to read ahead, you're doing the wrong thing, but of course I don't blame you. But you're sacrificing an opportunity to learn something. Get this result before you see me get it. If you get it wrong, then you know how to correct it. So what we know is that in this case, the current is the rate of change of the charge, and the voltage in the capacitor is charge over capacitance. What therefore is the function that gives the voltage across the capacitor as a function of time given this current? Okay, hopefully you've done both of those things. Now, it's fairly easy to work this out. Di dt, here's your I function. You take the derivative. Derivative of sine omega t is omega cosine omega t. It's very clear then that L di dt is L times omega times I max times the cosine of omega t. For the capacitor, I is dq dt, so that q is going to be an antiderivative of I. And whether you think of that as an antiderivative or just do it by common sense, what do you take the derivative of to get sine of omega t? Well, if you take the derivative of cosine of omega t, you get the negative of the sine, and you also get a factor of omega from the chain rule. If you take the derivative of the negative cosine of omega t, then you get a positive sine. You still got that omega from the chain rule, and you don't have an omega here. So let's take the derivative of 1 over omega, negative 1 over omega, times the cosine of omega t. And that gives you negative cosine omega t over omega. And then we have the factor I max here, and you can verify that the derivative of this is this. So the dq dt equals this. Alternatively, since I is a derivative of q with respect to t, then q is going to be an antiderivative of I with respect to t, and you can go into formal calculus and take that antiderivative, something you should certainly be able to do, and reconcile it with the common sense of my first explanation. Okay. Sometimes you get into much more complicated functions where a little common sense doesn't take you far. So you got to go into the formal calculus. But it's not really necessary here. It's good, but not necessary. Okay. Well, anyhow, now having this, then what is your capacitor voltage? You should pause with this function and figure out what your capacitor voltage function is going to be. Hopefully you've done that. You get capacitor voltage is Q over C. This is Q. Divide that by C, you get a C in the denominator here. So now we have voltage is negative I max over omega C cosine of omega t. Now, without looking too closely at the graphs I've made, I want you to graph I versus t and graph VL versus t. Remember that current and voltage have different units, so that the graphs are going to have completely different labeling, so it doesn't matter how you compare the amplitudes. You can have any two amplitudes you like. So they're not going to generally have the same amplitude, although you could graph them that way. But anyway you graph them, graph these two functions and see how far apart the two graphs are in the horizontal direction. How far apart are the peaks of one graph from the peaks of the other, for example. And then do the same for these two functions, the same current function, but the voltage of but the capacitor voltage function. Okay, well, hopefully you've done that. Now, here's a graph. If I of t is a multiple of the sine of omega t, then the sine of omega t has a graph that starts at the origin and starts in the positive direction and proceeds in the way that you're familiar with. What about the cosine of omega t? Well, it starts on the positive y-axis, decreases and increases, and moves along as the cosine does with the same period, because you have the omega t here and the omega t here. The period is going to be 2 pi over omega, basically. Now, question is now, how far apart are the peaks of these graphs? Well, the peaks of this graph occurs here. That's the voltage graph. And the peak of the current graph occurs here. That lines up with the zero of the voltage graph. But we see there's a 90-degree phase difference. In other words, omega t for the cosine function is 90 degrees different than omega t for the sine function. Now, is it plus omega t? Is it plus 90 degrees or minus 90 degrees? The thing that we want to focus on here, before we worry about whether it's a plus or minus 90 degrees, is the fact, well, which one hits zero first, okay? Or which one peaks first, okay? So you can figure that out. Well, hopefully you stop and do that. Ask yourself, which one is going to peak first? Well, you might seem that, well, okay, this one peaks, and then at a later time, this one peaks. Okay, so this peak occurs before this one. As this one is decreasing to its equilibrium, zero value, this one is increasing up to its peak. So the peak of the I of t graph occurs 90 degrees of phase later than the peak of the V of t graph. So V is 90 degrees ahead of I. Now, it might look like I is ahead of V since I is going this way, but, you know, every point along the t-axis is later than the ones before it. So, again, this occurs later than this. Now, if we go down to the graph for the capacitor, and hopefully you've done that, the graph of the sine function is the same as it was before. The graph of the negative of the cosine function starts at on the negative y-axis and increases, and the first place this graph hits zero is at the same point that the I of t graph, the V of t graph hits zero at the same point the I of t graph hits a peak or a valley. Okay, these points align. So now we have 90 degrees. Now if we're going from the V of t graph toward the I of t graph, we're going in the opposite direction as we were here. Okay, so that the V of t graph is now 90 degrees behind the I of t graph. So V's 90 degrees behind I. Now that's all very important. There's more, but I'm going to stop at this point and then we'll develop more of this idea.